Hello, welcome to our channel again. Suraj here, and after a long time, I'm going to post a video on the quantum mechanics. I'm going to continue our series of the quantum mechanics. So, my previous video was, I think, on the spin states, and now the video is going to be on the uncertainty principle derivation because most of you know that what exactly is the uncertainty principle, but the derivation of this principle is quite complex, not that much complex. So in today's video, this is our topic of deriving the uncertainty principle. So the basic mathematics that are required for this are the vector spaces, algebra, all that things, compulsory, and a bit use of the Dirac notations. I'm going to use Dirac notations. Although I have not made a video on the Dirac notations, but my next video is going to be on the maybe Dirac notations and the advanced mathematics of the uncertainty, of the quantum mechanics. So for now, we are going to derive it with the help of these types of mathematical tools, and especially the topic of the vector spaces, that here is the square inequality. Because when you do the inner product between the two vectors in the vector spaces, there is a inequality arising known as the square inequality, and that equality is our main in the deriving of the uncertainty principle. So we are wasting our time. Let's start our uncertainty principle. So most of you are familiar with the uncertainty principle. This is the general uncertainty principle. Change in x into change in momentum greater than it equal to h cut divided by 2. So this is our uncertainty principle. But this is not quite good because when you deal with the quantum mechanics, you all know that there is an expectation values of the different types of the observables. It means there is expectation of coming this value, this value. Although the name expectation value is very much confusing because expectation value, which means expectation, is quite different from what the values, the this particular of the momentums and the position will give. Okay, that's the video of another topic. But here, this is not quite good because this does not deals with the uncertainty. So this is the classical uncertainty principle. You can say that, not that much deep quantum uncertainty principle. But the uncertainty principle that we are going to derive quite complex, and it looks like this: sigma A. Okay, let's write here not sigma A. Sigma x into sigma p is greater than equal to h bar by 2. Here you can see that there are two differences. Here you can see that this is the change in x and change in p, and as you know that this is not good in the quantum mechanics because in quantum mechanics everything is like more probabilistic. So we have to deal with some probabilistic term, and here in the left hand side, the sigma x and sigma p, the probabilistic term that you are seeing, called the variance. So in general sense, a brief meaning of the variance is that it's like the spread in the quantities. It means, I mean to say that if you measure x precisely, then the spread in the x will be short because then the values are very precise, so that the spread in the values of x, you can see that if I make a graph like the x, then the spread of x is very low. It means you precisely know that what is going to be the value of x. But if you know the value of x precisely, it means the spread of x is very low, then the spread in momentum in the spread in the values of momentum will be great. What do you mean by spread? Spread means the value will be very great, varying from each other. It means you cannot determine a particular value. And that is the meaning of the variance. Variance measures this, that what is the spread. So if the spread in the position is less, spread means the precising values is very less. It means you are at the exact position in measuring the position of the particle. Then the momentum of the particle will be very much, you can say that, the spread here, and you can say that the values of p is not defined. It has several different type of the values, and you cannot actually determine that what values of momentum is going to be when we measure the particular exact position. And that is also the uncertainty principle. You cannot measure the momentum and the position of the particle precisely at the same and exact time. And if you do, then you are doing mistake, not the quantum mechanics. So let's start our discussion. How can I write the variance? So the variance of any particular quantity, let's say I've written the variance of A. So I'm assuming here our variance A. I will assume the quantity A. Please do not confuse, I'm only here taking A notation. to do the all of the calculations, and after this I will replace the value of A with our general position and momentum. So let's say I have to find general of sigma variance of A. So variance of A square in the Dirac notation is written like this: A operator minus this A, which is the expectation value sign, then here in the Dirac notation, sorry, psi here, okay, and here also A cap minus A expectation value, bracket, psi, then the Dirac notation's close. So this is general expression for finding the variance of quantity observable A. So just like this, what about another quantity? Let's say I imagine B square. So you can write the variance of this particular quantity in also similar fashion, bracket B cap minus expectation value of B, then bracket psi, then again B cap minus B expectation value, bracket psi, and expectation sorry, and here Dirac notation, this is called Bragg and Get notations. Okay, so this is how you are going to write the variance square of A and B respectively. And if you see carefully, this is nothing, this is just it means, if you can say that what I have written here, this Dirac notations is like the inner product between these two particular quantities, this and this quantity, inner product between these two particular quantities. And just like this, here also there is an inner product between this and this. It means I can imagine this particular quantity as F and this particular quantity as G, sorry, as also F. It means here is the inner product between the F, and that is called the norm. It means I can write this as F inner product. And just like this, what about our for B? So I can imagine this also as G and this also as G, and there is an inner product between the G and G. Now here is the role of the squarge inequality. So what is the squarge inequality? So squarge inequality, another important thing. The squarge inequality here, it's like that the inner product between the quantity F and F, just like here in our case, multiplied by the G and G inner product, this is a sign of the Dirac notation, is greater. Okay, so this particular quantity is greater than equal to taking the mod of the inner product between the quantity F and G. 1 minute, my writing is not that much good, sorry for this. Inner product between the F and G mod square. So this is the what called the squarge inequality. If you can see that this particular inner product between F and F is equals to the variance of A square, it means our left hand side equation can be written as, in a very simple fashion, as psi A square multiplied by psi B square, and it is greater than equal to the mod of the inner product between the mod of the inner product between the F and G whole square. Now we have to evaluate our right hand side quantity, which is, so we have to evaluate this term, which is the inner product between the F and G. So let's carry out the inner product. And let's choose the Another pen. So let's say yellow color. Okay. Now we are gonna do the inner product between the F and G. So let's see how we can do this. So here we have to first of all calculate the inner product F and G. If you remember, what's the F is? So if you remember, F is nothing. It's just the A minus A cap, which is operator sign, minus expectation value of A. Psi. This is what your F is, and G is also similar. For G, we have B cap minus expectation value of B psi. So let's do this. In Dirac notation, it's look like A minus, then bracket psi, this long, then B cap minus B operator, bracket psi, then Dirac notation. So this is how we are going to use the Dirac notation. Now let's evaluate this particular inner product. So for this inner product, I am going to put here psi and psi in the corners and doing out these all of the multiplications then. Psi, okay? Psi. Now we have to do here inner product A cap minus expectation value of A, and just like this here we have B. Oh my god. Just like this where we have, oh, writing. Just like this where here we have B cap minus B expectation value here and psi. Okay, now what we all have to do is that we have to just do the simple multiplications of this particular quantities and how we are supposed to do this. So let's evaluate like the simple multiplication rule. We have to just like this use this. I will try to improve my writing for sure. So let's multiply A cap and B cap. Here it will be like this. A cap, B cap. Then it will be minus A cap and B, bracket B. I will say here bracket B, it means the expectation value of B. Minus expectation value of A, which is bracket A, B cap, and minus minus positive A cap and B cap. Sorry, A bracket and B bracket. Here closing. Here also closing. Here A. Yes. Now here we have written our form. A bracket, sorry, A cap B cap minus A cap B bracket minus A bracket B bracket and all this stuffs. Now what we are going to do is to multiply this term again with the psi. Now here we're quite heavy mathematics, so let's see and carefully view. We have to multiply this A cap B cap with this particular psi and it will look like this. Psi bracket A cap B cap and psi. Understand? Just like this, negative of, what we have to do is that we have to just do this same for our second expectation value of B bracket expectation value of B bracket psi A cap psi. minus, then we'll take out a cap out after this inner product rule because a cap is in the inner product form, and then psi b cap psi, and then positive a cap and b cap psi and psi. Then psi and psi in inner product will be 1 because if you have studied, then it's normalized. Then psi and psi will be 1. That's why I'm not writing here. Okay, so for your convenience, I'm going to write it that this psi and psi, and as this there will be 1, it will look like this. Now, if you see that in Dirac notation, this is the sign of the expectation value. It means this particular term is nothing. It's just the a cap a cap multiplied by the b cap. 1 minute here. A cap multiplied by b cap expectation value minus b cap, sorry, b expectation value. And this is the in Dirac notation, this means the expectation value of a. It means I'm going to write it. It's like this, minus a cap, yeah, then it's b, just like this, expectation value of b, and then positive of a and b expectation value. So this and this will cut out. Exactly what we are left is with this particular form, which look like xb, a cap operator, which is a cap our operator multiplied by the b cap expectation value, and here it will be the negative of a expectation value, sorry, negative of a expectation value and b expectation value. So remember this result, okay? So this is for the f and g. Now we are going to calculate this same calculations, doing the same thing for g and f. And if you do this particular for g and f, it will looks like the same thing like this. The only thing will be the change in order of b and a, and it will does not make any sense. It means this particular thing exactly looks like this, but the only difference between the f and g and gef is the operation of these operators. It means in G and F, if you do all the calculation, you will end with this, that B cap is operating on A cap, and here is A cap is operating on B cap. This is the only difference, and all rest things will be just like the same. Okay. Now you will ask me that why I here I'm calculating F and G and F, because here in the square G inequality, if you will see that here is F and G, then why I'm calculating here the G and F also. So here I'm going to introduce one more idea that we are going to use here. Most of you are familiar with what exactly is the complex number. So if I let our complex number z as f and g, then why I'm letting it add an f and g? Because you know that the inner product between the two f and g is always a complex number, and z is also a complex number. Okay, now you understand. Now if I take the mod of the z square, mod of z square in the general form, how it's look like x square plus y square. Yes, yes, it's look like x plus y square. And this x square plus y square, x square plus y square is exactly can be written like this. But wait a second, why are we going to use this particular scenario? Because if x will be 0, then this particular quantity is equal to y square. It means mod of z square is equals to x square plus y square greater than less than y square. Now, if you see here, if you take z as x plus iota y, which is the general form of the, then its complex conjugate will be x minus I iota. So from this, how you can write the y? So from this we can write iota y is equals to x minus z complex conjugate, and y is equal to x minus z complex conjugate divided by iota. And this similarly y can also be written as, this similar y can also be written in the form of 1 by 2 iota, and here it will be z minus z complex conjugate, and here it will be bracket just like this. And if you do the squaring on both sides, y square, then y square is exactly equals to 1 over 2 iota the z complex number minus complex number, which is z complex conjugate whole square. So this is how y looks like. Z square is equals to x square plus y square greater than equal to y square. So why I'm using this concept here? Because if you remember here, we have let this particular quantity fg as y. It means y square here, y square is 1 over 2 iota z minus z complex conjugate whole square. And it means, by seeing all this, can I write this? Sigma x, sorry, x not, a is there. Sigma a square multiplied by sigma b square is greater than equal to 1 over 2 iota z minus z complex conjugate whole square. And if you watch carefully, if you have seen carefully, that z is exactly equal to f and g. And what about our z complex conjugate? So if z is equals to f and g, then z complex conjugate, of course, it will equal to g and f. And this substituting these two values in this particular equation, let's see what will happen. By substituting these values, let's see. Sigma a square multiplied by sigma b and its square greater than equal to 1 over 2 iota. Z is f and g, and if you see here, then the value of f and g is this, and the value of z and f is this. That's why I have calculated zf also. Okay, so I will put down all of the values of f and g and f. So according to my calculations from our upper section, we can write this particular thing as a cap b cap expectation value minus a expectation value b expectation value. This is the value of z, and minus we have to z complex conjugate, and z complex conjugate is g and f. And if you remember the value of g and f, it means g f calculation in a product is equals to b cap a cap minus this. And after doing this, it will be minus, it is b cap a cap minus a cap, sorry, a cap, no, a b expectation value. Okay, and then brackets closed, this. Now sigma A square multiplied by sigma B square is greater than equal to, if you see minus and minus minus plus, then this and this quantity will cut out, because if you open the bracket here, if you open the bracket, this and this will cut out, and what we are only left is with this, which is A cap B cap minus B cap A cap. Now here is the main part. Here A is the observable. So what if I put A observable as position, which is x, and B as momentum? What will happen? So let's see. Let putting the value of A as with is a sigma square and B as momentum. This will be P square greater than equal to 1 over 2 iota. I think one thing is missing. Okay, whole square. Okay, sorry, whole square and whole square. This was only missing here. 1 over 2 iota. Then this will be xp minus px. Operator sign I have to put on, because if I will not, then you will be confused. If you have studied quantum mechanics very carefully, then this is nothing. This is the commutation relationship between the position and the momentum, and the value of the commutation relationship between the position and momentum is written like this. I am going to written here with another pen, let's say green. 1 minute. Okay, so let's write down the commutation relationship between the x and momentum. The value of this is exactly equals to iota h cut. It means the value of this particular quantity is nothing but iota h cut. Let's substitute the value and let's see what will happen. Sigma x square, sigma x square, then sigma square p greater than equal to 1 over 2 iota, and putting the value of this as iota h cut, this will be iota h cut and square. Now what we all have to do is that take the root on both sides. If you take the root on both sides, this particular equation looks like this. Sorry, I have to put it down here. Momentum P is greater than equal to h bar or h cut divided by 2. So finally, we derived our Heisenberg's uncertainty principle, where h cut is nothing. H cut is reduced Planck constant, which is h divided by 2 pi. Finally, we arrived at the conclusion of the Heisenberg's uncertainty principle. The mathematics is quite complex and lengthy, but we finally derived our expression of the Heisenberg's uncertainty principle. And here, what we have done is that we have used the commutation relationship. Commutation relationship is a very great relationship. I'm going to tell you a fact about the commutation relationship, that if you have any operator, I'm saying any operator or any observable, let's say you have an observable A and B. If these two operators A and B commutes with each other, it means if you apply the A operator on B, and then subtract it by applying B operator on A, and if this becomes 0, then you can measure A and B simultaneously. But in the case of position and momentum, I have written here that it is equals to iota h cut, not 0. And this is the main reason why, and this is the, you can say that the beauty of the quantum mechanics, that by using the commutation relationship, you can say that you can see that which of the operators or which of the observables are going to measure simultaneously or not. Here in the case of A, B, if I apply A and on B, which means A must have some operator and P must have some operator, just in the case of position and momentum. Let's derive this, okay? I'm going to derive it to see you the, okay, so let's derive it for the position and the momentum case, how we can derive this. If you know position operator is x cap and momentum operator is the negative iota h cut h bar del by del x. I also made a video on deriving the different types of the operators. So you can watch this video on my operators and expectation values video on the quantum mechanics. Now what we have to do, x cap and p cap is there. The commutation relationship, let's see, x, p. Now apply the x operator, p operator, then must subtract it with the applying the momentum operator to the position operator. So let's see what will happen. You will be amazed. X cap, X, P cap is nothing, it's just negative iota. So first of all, you have to put down some of the functions on which you are going to apply this. So for test, I'm going to use the test function fx. And in this case also, I'm going to use fx. So let's erase this all. So that let's erase this. For operations, you must have some functions. So I'm going to write down our function. Fx as our operation function on which we are going to operate our operators. Okay, so let's see what will happen. Let's take our operator as fx. Okay, then you have to apply our xcop operator. Negative, you have to negative of iota h cut del fx del f by del x, let's say. Okay. Then negative of, I'm going to put here bracket to avoid the sign confusions. Now you have to apply the momentum operator, which is negative of iota h cut del by del x. And you have to apply this on two things, which is on x cap operator and p cap operator. Sorry, on x cap and not p cap. Oh, there's a mistake here. Okay, now. So you have to apply this on. Okay, so you have to apply this particular operator on two things. First of all is on the test function, and second is the position operator, which is x and f. You can use the derivative rule for this, derivative rule of differentiation. So how can I write that? This is negative x cap. So this is negative x cap iota h cut del f by del f del f divided by del x. Negative of, if you have to apply this, then the differentiation rule says this minus I h cut. Put down this as x operator and operate firstly on the del f by del x. Then it also will be negative and u iota h cut test function fx, and if you apply differentiate x with respect to the x, it will be 1, so this will be our final result. Now opening the bracket, now you just only have to open the bracket. So let's see what will happen. Negative of x operator iota h cut del f by del x. Negative, negative, positive iota h cut x cap del f by del x. And then negative, negative again, positive iota h cut fx. This and this will cut out, and it will be equal to positive, okay? Iota, here it will be equal to the iota h cut and our test function. So you can drop out the test function because it serves its uses, क्योंकि इसका यूज हो चुका है, तो टेस्ट फंक्शन को हम लोग एलिमिनेट कर सकते हैं और बचेगा हमारा आयोटा एच कट, और यही रिजल्ट मैंने यहाँ पे इस्तेमाल किया, that I used here in our derivation of the a b and minus b a. So as you can see that x and p is not zero, it means it do not commute with each other. It means we cannot measure them simultaneously, and that is the reason also why we can't measure x and p. Mathematical reason, because it's not equal to zero, not the physical reason. And this is today's video on the uncertainty principle. Hope you understand the commutation relationship and all that things. Next video is going to be on the mathematics, which is the vector spaces and the Hilbert spaces mainly, because I think the Dirac notations and vector spaces deep knowledge is very necessary in learning the high advanced quantum mechanics when you deal with the perturbations and the translation operator, the symmetries and the conservation laws. So this is for today's video. Thank you for watching my video. And I also have a Telegram channel, so you can join our Telegram channel where I post different types of the physics questions and also some mathematics question, but mainly physics questions of the Olympiad. So you can also check out that particular channel for the physics questions. So thank you for watching my video.